Generating 3D human motion from text alone has always been a game of compromise. You can tell a model to generate a high kick, and it will give you something that looks like a kick. But if you need the exact joint angles, the precise foot placement, or a specific trajectory through space, text quickly runs out of vocabulary. The semantic layer works beautifully, but the spatial layer is notoriously vague. That's exactly the problem DrawMotion solves. It's a new diffusion-based framework that introduces freehand drawing as a first-class condition for motion generation. Instead of forcing you to write paragraphs to describe limb positions, you can sketch a 2D trajectory for the pelvis path and drop stickman poses at arbitrary points along that path. The model then fuses this spatial guidance with text semantics to produce highly precise, physically plausible motion sequences. But implementing this isn't just about slapping a drawing module onto a text-to-motion pipeline. It introduces three fundamental challenges: generating training data for hand-drawn conditions, efficiently fusing heterogeneous conditions without blowing up compute, and aligning the generated trajectory with your sketch during inference without retraining the model. DrawMotion tackles each of these with a highly engineered architecture and a novel training-free guidance strategy. Let's start with the data. Existing motion datasets don't contain hand-drawn stickmen, so the authors designed a stickman generation algorithm. This algorithm projects 3D joint coordinates onto a 2D plane, simulating how a human would actually draw a pose. It accounts for real-world drawing artifacts, stroke jitter from different input devices, global misplacement, and scaling inconsistencies. To keep the representation computationally tractable, users draw 6 one-stroke lines representing the head, torso, and 4 limbs. Each line is independently encoded and aggregated by a transformer encoder into a single stickman embedding. The stickman encoder itself is pre-trained and frozen. It uses an autoencoder setup, where a feature-to-pose decoder reconstructs 3D joint offsets. Crucially, it employs a candidate loss that predicts multiple plausible 3D poses and minimizes the error for the best one. This handles the inherent ambiguity in 2D stickmen, especially when limbs overlap or the viewing angle makes left and right indistinguishable. The trajectory encoder, on the other hand, is a simple 1D CNN trained jointly with the main model, since trajectory points map directly to pelvis positions. Text is encoded using a frozen clip, VTB/32. Now, how do we fuse these conditions efficiently? Traditional diffusion models rely on masked self-attention to handle multiple conditions, which means computing attention weights across all token combinations and zeroing out unwanted ones. That's computationally wasteful and restricts how conditions interact. DrawMotion replaces this with a multi-condition module, or MCM. The MCM splits the batch into 4 segments representing all possible condition combinations: text with drawing, text alone, drawing alone, and unconditional. Instead of masking, it uses 2 lightweight decoders. The draw decoder uses standard dot product attention to fuse trajectory and stickman features with a motion sequence. This makes sense because drawing conditions are local and frame-specific. Dot product attention naturally captures cross-frame interactions and preserves temporal consistency. The text decoder uses efficient attention with linear complexity, which is better suited for global semantic control. The decoders predict offsets for their respective conditions. These offsets are summed along the batch dimension, and the fused features are re-encoded by a latent encoder before passing to the next MCM layer. This design cuts computational overhead significantly while improving condition alignment. The base model uses DDIM for the reverse diffusion process. It's deterministic, which accelerates sampling and gives us more stable control over the generation trajectory. During training, the model minimizes a unified loss combining trajectory alignment, stickman pose fidelity, and standard motion reconstruction. The trajectory loss ensures the generated pelvis path matches the drawn curve, while the stickman loss enforces frame-level pose accuracy using a binary mask to handle varying stickman placements. Here's where the architecture gets really interesting. Even with perfect training, text semantics and spatial trajectory constraints can fight each other during inference. Text might push the motion toward a generic interpretation, while your drawing demands strict spatial adherence. Existing solutions either require additional training loops or backpropagate gradients directly into the noised motion or initial noise, which often breaks the data distribution and produces unnatural artifacts. DrawMotion introduces intermediate feature guidance, or IFG, a training-free method that updates the MCM's intermediate features directly during inference. The authors discovered through PCA analysis that the intermediate features produced by the MCM's condition fusion module don't collapse into discrete clusters like traditional models. Instead, they form a continuous, high-dimensional manifold. This continuity is key. It means we can perturb these features with gradients without pushing them out of the valid generation space. The IFG process works like this. At a given diffusion step, we extract the intermediate feature map from the MCM. We define a spatial loss that measures the distance between the predicted clean motion and the user's trajectory constraint. We then backpropagate this loss directly into the intermediate features using stochastic gradient descent. But we can't just update them freely. If the learning rate is too high or the update is too aggressive, the features drift into low-probability regions, and the model generates garbage. To prevent this, DrawMotion uses Mahalanobis distance clipping. During evaluation, the mean and covariance of the intermediate features are estimated. The Mahalanobis distance measures how far a perturbed feature is from this statistical distribution, accounting for feature correlations. If the updated feature crosses a predefined Mahalanobis boundary, the gradient update is clipped. Only a small fraction of the out-of-bound update is retained, allowing the feature to explore new directions without destabilizing the generation. This keeps the motion vivid and distribution aligned, while strictly enforcing trajectory alignment. The result is a hybrid guidance system. Training-based conditioning handles the heavy lifting of fusing text and drawing, while training-free IFG refines spatial alignment at inference time with minimal compute overhead. No extra training, no ControlNet, no multiple noise reoptimization passes. On benchmarks like Human ML 3D and KitML, DrawMotion achieves trajectory error and Stickman similarity scores that significantly outperform both text-only baselines and existing training-free motion editing methods. It maintains competitive FID and ARP precision, proving that precise spatial control doesn't have to come at the cost of motion naturalness. In user studies, the drawing interface cuts generation time by nearly 47% compared to iterative text refinement, and professional animators note that the AI-generated trajectories are far more efficient than manual keyframing while preserving higher motion quality. There are limitations, of course. If your drawn trajectory violates basic kinematics or directly contradicts the text prompt, the model will struggle to reconcile the conflict. The guidance loss can actually be exposed to the user as a feedback signal, helping you tune your sketches before generation. But overall, DrawMotion demonstrates that freehand drawing is a viable, highly efficient control modality for generative motion. The paper and code are publicly available, and the architecture opens up new directions for interactive, fine-grained motion synthesis. If you're working on diffusion-based generation, condition fusion, or training-free guidance, the MCM design and the intermediate feature space analysis are worth studying closely. It's a clean example of how understanding latent space geometry can lead to practical, compute-efficient guidance strategies. Check out the repository, experiment with the multi-condition fusion, and see how drawing changes the way you interact with generative motion models. The research is out there, and it's already pushing the boundary of what's possible when you let users draw their intent directly into the generation loop.